what you need to know about clouds. So one of the things that we talked about Monday, we said that, like the video said, cold air holds less water. And what we mean by that is less water in its gaseous phase. So that water in its gaseous phase and cold temperatures will condense or form liquid. That's it. They'll reach 100% relative humidity. So chunks of air, we're going to talk about different ways of getting a chunk of air to rise, but assuming, and we're going to talk about 4, assuming you get to rise, it will get larger and it will, as it expands, it will cool. Now, you probably heard of like weather balloons, okay? Weather balloons are like a big old latex. It's kind of interesting how they do this. They go up all around the world twice a day, about the same time, weather balloons. And they carry with them like a gizmo, a box, that gives us different conditions at different elevations. So my point about a weather balloon is it might start out this big, but as it goes up in elevation, and we'll talk about why this would be, but it gets larger and larger. The reason is because the air is thinner up there. Have you ever heard of climbing a mountain, and if you're an athlete, you have issues? So there's less pressure up there, less oxygen, less nitrogen, and so the weather balloon expands about the size of a house. And then the latex bursts, and then the little gizmo that carried the data to the person who was looking at the information, it has a cute little parachute and it falls back to the ground. And it can be reused. One on my bucket list is to find one of those things, one of the little boxes. And I'll probably give it back. But anyway, so things as they rise, air as it rises, it will expand and will cool. So as it cools, we can reach 100% relative humidity, and we talked about that on, this is Wednesday, on Monday. We talked about how that kind of works. So how are we going to get a chunk of air to rise? Well, here's one. And actually, if we consider this this could be California. This could be the Pacific Ocean. Of course, we have Atlantic Ocean over here. We are under the influence of a westerly, what we call mid-latitude westerly wind, prevailing wind. So anyway, if you get a chunk of, all wind is moving air. So if you get moving air, moving from the west to the east, once it hits the, what are these, the Rockies, okay, Sierra Nevada range, once it hits the mountain, it will be forced up. We call that orographic lifting. So again, you know, these 4 things I talk about lifting a chunk of air, if that chunk of air has humidity, if it has water vapor, there's a possibility it could go ahead and condense and give you clouds. Okay, so anytime you see a cloud, think of liquid water. The next one, and we'll be talking more about this in part 2, which I'm hoping to get to. The other day, I pulled up a weather map, and you told me the blue lines with the triangles were cold fronts, and the red lines with the semicircles are warm fronts. So we'll talk more about what a front is, but do our cold fronts come from the north or come from the south? They come from the north, yep. So, yeah, I don't have red, but so your cold front is going to look like this. And if you're colorblind, it's nice because we even have a symbol here, they're triangles. So all cold front is you have cold air here and warm air here. So our warm fronts are going to come from the south, and they are going to have, they won't be blue, they'll be red, and they'll have semicircles. Okay, so here you have warm air here and cold air here. And these are 2 different scenarios, so that's not going to clash. But where we have a difference between air masses, we have a potential lifting mechanism. So which would hug the ground more, cold air or warm air? Cold air is going to hug the ground more because warm air rises. We know that happens in our houses and stuff like that. So cold air is going to hug the ground, and you can kind of see that here, cold air hugging the ground, okay, warm air being pushed up. So that's another way of getting chunks of air rising. The other one can happen on just a normal sunny day. Now, this goes back to, I don't know if we've talked about this in here, but if it's summertime and it's like gonna be 95 today, what color t-shirt do you wear? You wear a white or light color t-shirt, yeah. So the thing about it is light-colored things will reflect sunlight and dark-colored things will absorb sunlight. So here we have an area that's absorbing sunlight, absorbing thermal energy, and this little kind of contact lens looking thing, that's a blob of air that's getting heated up. And what do we know about warm air? It's going to rise. Yeah, we call that convection, where it's just kind of rising because it's warm. It's less dense than the surrounding air. So convection. And then the last one, of course, well, we don't see a lot of this here, but it's called convergence. And this kind of makes sense. Well, let's see, how can I show this? It's a friction thing. Maybe I can show it up here. Trying to see if I can make a ramp out of this. Assuming, I don't know if it's going to work. This blipper gets a lot of pain throughout the semester. So I'll demonstrate instead of pushing it. But this is slicker, right? Okay, this is rougher. Well, it feels pretty slick too. Assuming something is rougher. And just like kind of showing the water coming from the ocean and going onto land, it can go faster here. What do you think about here? It's going to slow down, yeah. And so kind of we have a bunching up, okay? And that's exactly what we call this last type of lifting. It's convergence. So it bunches up, it goes fast, and then it kind of has to slow down and it bunches up. That's it, convergence. Years ago, I went to Florida for spring break. And it's true, man, they have some crazy sort of weather down there. I don't know. It's like kind of quick showers that come and go. Okay? So these are what we say 4 different ways of lifting air. And again, if you can lift the air, it will expand, and as it expands, it will cool. And as it cools, if there's water vapor, you can get clouds. Okay? No water vapor, no clouds. So most of the time, a lot of times, clouds are drawn with a flat bottom. Now, the video we watched kind of showed a cloud that was a little kind of, he was funny. But a lot of times clouds will have, and you'll see this actually in nature, you'll kind of see a nice distinct location where there is no cloud, and here there is cloud. All right? So this part right here, I'm going to erase my front here. This elevation, if this is the land, okay, this elevation right here, okay, was how far you needed to take that chunk of air to rise, expand, and cool, and to begin condensation. That's what we call the lifting condensation level. This is so awesome. Clouds usually have flat little bottoms. Okay, the older the cloud, the more you can kind of get a little fuzzy here. But that is the LCL, lifting condensation level. I have a little video to show you that. LCL. Looks like I just revealed an LCL there. Okay, let's watch this little video. Different precipitation types. Now, by definition, I think one of the videos we watched says it has to literally fall from the atmosphere and hit the ground. That's only precipitation. So we can kind of talk about 4 different types of precipitation. Where there is surface, it has to fall from the Earth's atmosphere and hit the Earth's surface. Can't believe we have snow in the forecast for Sunday. Are you serious? And it's a French word called bourgeon. The bourgeon process is the kind of the formation of snow, basically, in the atmosphere. Snow, you know, if we try to freeze water, we don't get snow, right? We get ice cubes, right? So there's got to be something else awesome going on up there. And there's a lot more to it, but I'm just going to throw out the term bourgeon process. Here's a cute little snowflake. Now, of course, those red dots, those red circles with the 2 little white antennae, those are water molecules, oxygen and 2 hydrogens. This is water vapor here, and the little blue orbs here are liquid water, and of course, that's a snowflake. And it's kind of a big, hairy deal, but basically, I don't know if you can tell, but we see the gas going right from the gas into the solid snowflake. And we call that word, starts letter D. It's the opposite of sublimation is when you go to the bank, you make a deposit. Yep, so it's deposition. Yep, that's deposition. Cute little snowflake though. So this is where I say that, like even especially in the springtime and maybe even the summertime, one of the things, what happens to temperature when you climb a mountain? Does it get colder or warmer? It gets colder. Yep, when you climb a mountain, it gets colder. And in this layer, which we're going to call we layer the Earth's atmosphere, and we're going to call actually this layer, it's going to be called the troposphere. But as you get up, it gets colder. Yep. So my point is that a lot of times what falls as rain, here's my raindrops, actually started, here's my flat bottom, actually started out as, here's my snowflake. Okay, so why do we get rain instead of snow? What do you think? It melts. It melts, exactly. Down here, it melts, exactly. You got it. And what's that transition temperature? What temperature does water melt at? 32. Yep, 32. Yep. So here in a minute, you're going to see some kind of temperatures, and I could put 32 degrees Fahrenheit, right? What is it in the Celsius scale? Do you remember? 0. Yep. Or 0 degrees Celsius. Yep. That's when you're going to get rain. Otherwise, it's snow. Okay. So, you know, when you're thinking spring is here, you're like, well, it started out as snowflakes, probably. Okay. This actually is what I just put on the board there. Okay, so you see, anytime you see a cloud, I'm hoping you think liquid water, but actually here, you should be thinking solid water, right? Liquid water or solid water makes it non-transparent, because otherwise water or vapor, water gas is transparent. So anyways, yes. Here's another scenario. You know, what's the difference between these two? No rain, and how come? It's cold, exactly. That's the only deal. But can you kind of see, just as the few little temperatures, can you see where it's getting colder as you go up? So we're talking 59 Fahrenheit, 32 Fahrenheit, 14 Fahrenheit. So it's getting colder as you go up. Well, the other two I need to talk about are not near as, well, snow isn't fun to me. I get all stressed out with them. But I need to talk about freezing rain and something called sleet, actually freezing rain and sleet. So here we go. You need what's called a temperature inversion. So one way to think of it is, if for this scenario, this is normal, this is no temperature inversion. And if I was to have like a little chart here of temperature, okay, versus elevation, okay, where this is cold temperature and this is warm temperature, I would start down here and I would get colder, colder, colder as I go up, right? Okay, so that's normal. A temperature inversion does this, where I get, how does this go? Make sure I do it right. I have colder air. Yep, I have a kink in it. Okay, instead of having, this is what we call a negative slope, I actually have a positive slope down here. So I've got this, that's my kink, and then I have it normal right here. Okay, so this is a temperature inversion. You're like, well, that doesn't look too bad. Totally. But this is cold, this is elevation, okay, and this is warm. The problem is if you have, let's see, we're going to make this right here 32 degrees Celsius, or 32, oh goodness, 32 degrees Fahrenheit, freezing. Can you see where here it starts out as snow? Right here, it's warm and it melts. And then what's it do right here? It freezes, exactly. So temperature inversion sets you up for some sort of refreezing of liquid water. That's it. Temperature inversions. So this is, you can kind of see, let's see, how's it go? Blue represents where water is going to be, it's colder than freezing. The pink here represents where it's melted or warmer than freezing. So can you see where we actually have a pocket of cold air under the pocket of warm air, which this is not right. Okay, this is a temperature inversion. Okay, and depending upon the depth of the temperature inversion, now only two difference here. By the way, this is sleet and this is freezing rain. So when it says glaze, you're going to have to kind of think of freezing rain. What's the difference between these two? They're both temperature inversions. I guess I would just say kind of how deep that cold pocket is. Like here we have it's pretty deep, yeah, and it pelletizes. Is that a word? It actually reforms little pellets. Sweet. And then here it doesn't have time to repelletize, but it freezes on contact. Okay, so both bad. Sleet's a little bit better. Freezing rain or glaze is really dangerous. So anyway. We're going to clear probably near the end of meteorology. We're going to talk about severe weather. Now, some of you guys know that with a thunderstorm, sometimes you can get hail. Okay, I'm going to try to convince you that hail, it's pelletized. It's pellets too. Okay, hail is pellets too, but it is nothing like sleet. They look like they're the same, but they are totally different. I'll try to convince you of that. So what about warm clouds? So cold clouds, actually let's go back here. Wow, these are all cold clouds. They have the Bergeron process going on. Why is that? Well, because I can see snow falling from them. Okay, well what about warm clouds? It happens, especially near the tropics and in the summertime for us. Well, it takes on a little bit of a different pattern. The happy cloud we saw starting this kind of talked about water vapor forming or clustering around an aerosol or something like that, piece of dirt, small, I don't know what they called it in the video. That little piece of dirt or whatever is important, especially in getting liquid water to form in these clouds. That's called a cloud condensation nuclei. Okay, so kind of think of these little orbs now. These orbs are liquid water. Those orbs, to me, would probably have been seeded by cloud condensation nuclei. Okay, and so after they the cloud condensation nuclei kind of gets liquefaction to begin. Okay, assuming you're at 100% relative humidity in that region anyway. Then we have kind of assortment of sizes of cute little drops. The larger the drop, the faster it falls, and it will gobble up little ones as it falls. So it's kind of neat. I've seen videos on it. Okay. So as the big one, which we call the collector drop, okay, the thing that's going to fall from the cloud, as the big one gathers up the little ones, we call that collision because it collides, because the big one's falling faster than the smaller ones, and coalescence because it gets bigger. Collision, coalescence. Okay, so you can kind of see from A to B, your collector droplets getting bigger and bigger. And, you know, as I reach up here, if this is like the base of my cloud, not all clouds rain, do they? Not all clouds rain. So it's kind of, as I understand it, a mass sort of thing. Only if these get massive enough will they fall from the cloud. Which suggests that there's something kind of, and it's called an updraft. Actually, we have a kind of a slow-moving updraft, and it's like, you know, beam me up, Scotty, but really, there is an updraft going up at all. It's subtle at all times. But when the cloud droplet is massive enough, it will fall. And then if I were to be able to animate this, I've seen videos where it kind of gets bigger and bigger, and it kind of gets wobbly, and actually our collector droplet can break and form, you see it forming 5, this big one broke into 5 new ones, and it continues the process now. Okay. All right, cool. So on your test somewhere, it'll probably be a figure that's on the next slide where I ask you about these 10 cloud types. There's different ways of chunking them up, but I think this works pretty good. So there are flat ones we call stratus. And there are fluffy ones we call cumulo or cumulus. Cumulo or cumulus. So if it's flat. Okay. And here in a minute we'll go to the window. Maybe we won't, but just remember when you came in. Do they look pretty flat? They look flat to me. So right now there's a type of stratus cloud up there. Well, the other thing we need to do is kind of describe what general elevation the cloud is. And basically they take this layer of the atmosphere and they chunk it up into kind of 3 regions. We have the lower region, okay? And if it's kind of a relatively low cloud, it's going to get no prefix. If it's in the middle region of the troposphere, it's going to get an alto prefix. And if it's an upper one, it's going to get a cirrus or cirro prefix. So that's it. And there's actually one other criteria. So we have, is it flat or fluffy? What elevation is it? So we kind of mix and match those 2 things. The other one is it actively dumping water? Is it precipitating? If it's precipitating, we're going to give it either a nimbo or nimbus is going to be part of its name. So those are 3 things. Flat or fluffy, general elevation, and is it precipitating? And we get 10 cloud types. So here's our 10 cloud types. To me, what I see out there right now is just kind of a stratus cloud. Stratus, notice we don't use an alto or a cirro or anything like that. It's because it's a low cloud. All right, so the word is high. High clouds. What are our options for high clouds? Well, we can have the high flat cloud, or let's start with the fluffy. We can have the high fluffy cloud, which is cirrostratus. Oh, sorry, darn it. Fluffy, drat. Cirrocumulus. Final answer. High fluffy cloud. Let's see. Sometimes this is called a mackerel sky, like as in the fish. I don't know how to spell mackerel. Okay, little tiny cotton balls. Mackerel sky. Cirrostratus. Also up there, we've actually got now 2 layered clouds. We have cirrostratus, cirro meaning high, stratus meaning layered or flat. And then we have cirrus, which is the way high one. Cirrus, these are sometimes called mare's tails, like the horse, mare's tails. Okay, so there we have 3 high clouds. Then we have a couple of middle clouds, only two middle clouds. Here we have the middle, since they're middle, we're going to go with alto, since it's middle, so we have an alto flat, alto stratus, then we have an alto or middle fluffy, alto cumulus. And this guy right here, instead of the mackerel sky would be tiny because they're way high up. The alto cumulus will look like cotton balls. They really do. They do. So that's your 2 middle one. And kind of the rule of thumb is, no pun intended, but if you stretch out your thumb, your puffs in alto cumulus will be about the size of your thumb. Stretch out your arm, then the mackerel sky, your high up ones will be about the size of your pinky. Okay, then we get down to the low clouds. We've got an assortment of those. If you stretch out your arm or whatever, stretch out your arm or hold it up to the cloud, and if the cloud's about the size of your fist and it's fluffy, then what you have is some sort of probably cumulus cloud. Okay, so cumulus meaning there's no alto, it's not middle, there's no cirro, it's not high, it's just cumulus. So it's a relatively low cloud, again, about the size of your fist. Also low clouds, we have, I mentioned, I think we're looking at stratus out here. I think it might be alto stratus. I don't know, stratus or alto stratus today. You can kind of check what you think. It's hard to tell. And then we have a couple of precipitating clouds. Oh, sorry. One is that drives me nuts is stratocumulus. Because it sounds like an oxymoronic sort of cloud. Because I said it's either stratus, it's either flat, or it's cumulus, it's fluffy. Stratocumulus, like you can see, kind of straddles the low and the middle cloud, and it's got some flat and some fluffy to it. Really? Okay, so precipitating clouds. There are 2 types of precipitating clouds. One of them is low, nimbostratus, and the other one is the one that gets my anxiety going. It's the storm cloud. the storm cloud, the cumulonimbus storm cloud. Okay. Now, what elevation is the cumulonimbus? Well, when I look at this, I'm looking low, middle, and maybe even high. Cumulonimbus has what we call a lot of vertical development. It's just a monster. Well, it's not really, but okay. So those are the 10 types. So clouds with significant vertical depth. Although, to me, which looks deeper, cumulus or cumulonimbus, the cumulonimbus looks like it's got a lot more depth to it. And with that depth comes some dynamics that actually then give us lightning and hail and tornadoes. All right, so here's some pictures. Starting with the high clouds, this is the mackerel sky, kind of the little, about the size of your pinky. And all cloud types have like a 2-letter designation. So, yeah, this is cirrocumulus. Cirrostratus. I wonder what anyway, I call this cirrocumulus. I'm going to dim the lights a little bit. You may have seen either around the sun or the moon a circle. And there's 2 types of circles. There's the circle that doesn't touch the sun or the moon, and that's kind of what this is. So this actually is a halo. And we can see halos around the moon too, the same around the sun. And it's caused by a little bit of science going on between the light that's coming and the cloud that is in between the sun and us. So, pretty. This is a middle cloud, middle layer cloud, altostratus, and it has a little bit of ripple to it. This would be about the size of your thumb. This is like the cotton balls, altrocumulus. Stratus would be low level and flat. We're going to talk about fog on the next slide. Almost looks like fog, doesn't it? Cumulus would be about the size of your fist. And, this looks like it's a little bit of vertical development. Looks like it's not precipitating, so it's not a cumulonimbus, but it looks like it could develop into something. And stratocumulus. Drives me nuts. Relatively low cloud, kind of between the low and the middle, and it's flat with a little bit of fluff to it. Now, it's quite possible to go out on a given day and to see an assortment of cloud types because they're caused a little bit by different pockets of moist air. So precipitating clouds, nimbostratus would be precipitating because we have nimbo, stratus, flat. So a lot of times in the wintertime, we get precipitation from nimbostratus clouds. Even in the summertime, if it's an ongoing rain, that's probably what's giving it to us. Cumulonimbus clouds, the precipitation is different it feels different. It's more short-lived, and again, we have a bit of vertical development associated with it. All right, fog. So fog is like a stratus cloud, relatively low level. This radiation fog is like, I think, the ones that kids hope for when they go to bed, radiation fog. And the reason they call it radiation fog is at nighttime, basically the Earth radiates the energy it got from the sun. So the Earth cools down at nighttime. We all know that, okay? Well, it can, depending upon. So this sort of condition then gives you that the coolness that you need to go ahead and have condensation happen, create your fog. Advection fog then is when warm, moist air moves over a cold surface. And a good way to get warm, moist air would be your oceans. So you can kind of get a sense for if that looks like a fancy bridge. It is. So that's advection fog. Upslope fog, to me, is kind of like a little bit ago I showed you. You can take air and slam it against the Rocky Mountains, If it goes up, we call that orographic lifting. And it also can create this kind of cool fog. We just call it upslope fog. And then the last one, it kind of reminds me of something you might see, we might see around here. Even over the moving rivers, I've seen this bit of hovering fog in the morning sometimes. And it's called evaporation fog. And basically the reason it's called evaporation fog is water is great at like sucking in energy. I mean, like, for instance, if you get your swimming pool that you have in your backyard, it's got some depth to it and nice and warm. If you go out there at midnight, it's still probably nice and warm. So basically, water holds or retains its heat. And so what can happen is it can go ahead and add a little bit of vapor to the region above it, and the region above it cools off, and it gives us this sort of evaporation fog. Evaporation fog is what you have in the mornings when you take a shower, assuming you take a shower, because you have little droplets that are created by your shower mist, and it comes in contact with the cool bathroom, and it creates this evaporation. Okay, so on to fronts, or air masses and fronts. This topic people do pretty well with. And at the end of this part is the homework that actually goes for part 1 and part 2, I think, anyway. All right. So, an air mass, how big are we talking? Well, we're talking about the size of a large state. And I've heard it likened to, if you were to travel abroad, like go over to, I don't know, somewhere in Europe where they have a fancy accent, and spend like a month over there, you would pick up their accent. Probably a little bit, you know it. And so that's kind of similar to a chunk of air who just sits over what we call the source region. Now, if that source region is hot, it's going to kind of become warmer. If that source region is wet, it's going to become moist. So that's kind of what we mean about source regions and air masses being formed. Okay. So it stays stagnant. Of course, stagnant means, well, if you have stagnant water, you have water that's not moving. Okay, so that, just like you would go to, like I said, Europe, spend a month or so, okay, it needs to hang out. Not necessarily a month, but a couple weeks. And the place where it's hanging out, we call the source region. And so, my maps of the United States are terrible, but it doesn't stop me from drawing them. On the next page, we're going to see source regions, but just intuitively. You know, if this is my Florida, oh my goodness, Mexico-ish. Okay, Canada, okay. Just intuitively, if a chunk of air hangs out up here over Canada, okay, it's going to be cold and dry. If a chunk of air hangs out here, it's going to be warm and moist. That's it. Those actually are 2 source regions. That's kind of how that works. Okay, so an air mass types are based upon where they hang out. Air mass types are based upon the source region they form over. And it kind of reminds me of the clouds a little bit in that we have 2 criteria we put together. And with clouds, it was like, what, flat or fluffy, elevation, and was it precipitating? So there's 3. Here there's just 2. We're going to use a lowercase c to talk about continental air masses. And continental air masses is a chunk of air that stayed over a continent, hung out there, and that continent isn't a large body of water, so it's relatively dry. Maritime, a lowercase m, means that, and this would be an example of maritime air mass, okay? If it stayed there long enough, it would take on the characteristics of return warm and moist. So those are 2 options for moisture. Okay, then we have some options for temperature. So moisture and temperature, the 2 things put together. The temperature are capital letters. A capital T means tropical. So to me, this guy down here, I say warm, but I probably call it tropical, because the equator's down here. Okay, so the way this works is, and we put the moisture first. So this guy would be an MT. Maritime, because it's over the Gulf. T, because it's hot. So another temperature possibility, and actually I'm going to do this one with the Canada one. Okay, so first I have to say, what do you think? Is this maritime or continental? I'm going with continental. Okay, do you think it's tropical or polar? Yep, that's it. That's all that works. Yep, continental polar. Now, there is one more possibility, and it's very cold air. If you've ever heard the meteorologists kind of, and I don't know how meteorologists feel about the weather. I don't know, it's their job, but they like say, well, there's an Arctic air mass that's going to influence, or Arctic air mass headed our way. You know it's very cold. So up above here, I could do another circle, and that would be A for Arctic. Now, Arctic, as far as what I think, is we don't say if it's dry or moist, because if it's Arctic, if it's very cold, how much water moisture you got? Not much at all. So Arctic air is relatively dry anyway. Okay, so source regions. Okay, you need to say what the moisture is, whether it's continental or tropical, or excuse me, continental or maritime. Maritime or moist, okay, or sea, or continental means dry. And then they also need to give an indication of the temperature. So temperature-wise, the ones that line up with maritime and continental, your options are going to be polar or tropic. So that's kind of how it goes. So here we go. Here are the six air mass source regions. So you kind of see the United States there. The first one, I told you the Gulf was a source region for maritime tropical air. Here we have the Atlantic, here we have the Pacific. And you can already, well, they don't look like arrows, but what I'm going to kind of show you, or what you need to know, is that those air masses, after they pick up their accent, they can actually catch a ride and start moving. That's where you know they have an accent. Like if you stayed in Europe, they wouldn't know you have an accent. You leave Europe, that's when you know. Okay. So source regions for maritime tropical are here. Source regions for continental tropical. Continental meaning dry, tropical meaning warm. Warm or hot, that's okay either way. And there's the source region right there. So continental tropical, our only source region for us anyway, is right here over Mexico. Then we have maritime polar. Okay, maritime meaning moist or some sort of ocean, large body of water. Polar meaning relatively cold. So here, in kind of the northern part of the Pacific, we have a source region. And here, over here, in the Atlantic Ocean, we have another source region, maritime polar. Right? What else we got? Continental polar. Continental polar I kind of drew over here. Continental polar, continental meaning it's over a continent, so it's relatively dry. Polar meaning it must, for us, be coming from the north or located in the north. Yeah, and I do in this textbook break Arctic out into two, so sorry about that. So if I break Arctic out into two, we've got a maritime Arctic, and then we've got a continental Arctic. The continental Arctic I have shown that could affect North America would be over Greenland. So notice I do go ahead and have a little asterisk. With regard to maritime Arctic, I have 2 asterisks, and that's maritime Arctic are not very likely to form because they'll sit there but won't pick up much moisture because it's cold. Last So this is a favorite one to put on a test with like a diagram or like a figure. And we don't have it. We're on test for a few weeks. Tomorrow's lab we're gonna measure humidity. All right. So weather fronts. Weather fronts are kind of like military fronts. Like a military front, you figure you have armies on both sides and they're clashing. So what happens for weather front is you have 2 air masses that are meeting up. They form a line between them. And those are the lines we've been drawing. Those weather fronts, the cold front, 2 air masses. Warm front, 2 air masses. So we talked about different types of lifting mechanisms. If you can get a chunk of air to lift, that chunk of air will get larger, expand, and cool down. And if there's water vapor, you can get it to cool down to the point where condensation begins at the lifting condensation level. But anyway, so one type of lifting mechanism was frontal lifting. So the fronts are named for the one doing I call it the aggressive air mass, the one doing the pushing. So when we talked about a cold, the cold front, okay, and I'll do little triangles here. That must have been the cold air mass doing the pushing. Now, was there warm air mass here or warm air here? Yes. But it was the cold air that was doing the pushing. Oh, warm front. Okay, so a warm front is a red line with semicircles. A cold front is a blue line with triangles. Looks like I wasn't being careful about my orientation here. You know, in the northern hemisphere, our cold fronts. You wouldn't see a cold front like this, because to me it looks like it's pushing from the south. The direction where the triangles or the semicircles are is showing you where it's going. So this actually should look like this. Stationary front, and actually today I looked at the weather map before coming today, and we had a stationary front there, which means like a truce has been called, and you have. If there is a stationary front, it will look like this. You'll see a triangle here, and you'll see a semicircle here. Triangle here, semicircle here, triangle here. That's an indication that you have cold air here, it's pushing, but you have warm air here, and it's also pushing, and it's a standoff. No one's winning out. And the last one, somebody asked about the other day. Generally, it's like a purple color. And you can tell the difference. What's the difference between stationary front and include front on the weather map? How could you tell these if they weren't colored? Yep, it's like one of those weird tests. Yep, the triangle circles are on the same side for an include front. Okay. Well, we'll pick up there when we meet again on Friday, but don't forget about last mark. Thank you.